So now we're going to look at how we can use something called bond enthalpies or average bond enthalpies and apply Hess's law to calculate enthalpy changes for reactions. So if we look at the definition of mean bond enthalpy, the definition is the enthalpy change when 1 mole of, and here it says a specified type of bond, is averaged over different compounds. So what we mean by mean, it's an average taken from the same type of bond in a range of compounds. So for example, if we look at water here, OH, in the OH covalent bond, the OH covalent bond is present in water, it's present in alcohols, but the value of it will differ slightly in those because they've got different environments. So notice that all of these values are endothermic. That is, energy is needed to break the bond because you're overcoming the electrostatic attraction between the oxygen nucleus here for the pair of electrons that it's sharing and the hydrogen nucleus for the pair of electrons it's sharing. So to break any bond, energy is required. It's endothermic. You need to put energy in. So therefore all mean bond energies are all positive because you need to break a bond. So conversely, if you're going to make a bond, you're going to get electrostatic attraction between two atoms. So here, say we've got an oxygen with its unpaired electron and a hydrogen with its unpaired electron. You've got the mutual attraction between those two atoms, and therefore to make an OH bond, energy is going to be released. It's going to be exothermic because you've got electrostatic attraction. So to make a bond, energy is released. Therefore, mean bond enthalpies are all endothermic, energy requiring. So now let's have a look at an energy level diagram, and then we'll turn this back to the Hess cycles that you're used to. So say for example, we've got some methane and we're going to burn it in oxygen, and there's two routes to this process. So one route is to completely burn the methane in oxygen to form carbon dioxide and water. And you know, for any combustion process, it's exothermic, heat energy is being released. So this is in effect the enthalpy of combustion. The arrow's going down because the products have got less energy. The carbon dioxide and water have got less energy than the reactants, the fuel and oxygen, so they're lower down there on the energy level diagram. So if we move on, what we're effectively doing is we're breaking all of the bonds in the methane molecules and all of the bonds in the oxygen molecules to release the free atoms in the gaseous state. So one route would be to completely combust, or the other route is to completely atomize all of the molecules, and then those atoms could then recombine to form the products. So what you can see in this route, breaking bonds requires energy. So here the enthalpy change has a positive sign because we're going up. It's endothermic, it's taking in heat energy. And therefore, when we're now forming bonds, we're now making the products, we are making bonds, and this reaction is therefore going to be exothermic. It has a negative sign because you're forming lots and lots of electrostatic forces of attraction. So breaking bonds, you're putting in heat energy, it's got a positive enthalpy change, and making bonds is exothermic, that's got a negative enthalpy change. Lots of heat energy is being released due to all those electrostatic forces of attraction between the atoms. So now the best thing to do is, if we now look at the reactants, the first thing you should do is to draw out the bonds. So methane, you can see, has got 1, 2, 3, 4 carbon hydrogen bonds, and oxygen, remember oxygen goes around as dioxygen, which is 2 O double bond O's. So if we look at in more detail, there are your 4 carbon hydrogen bonds in your methane, And then here are our two, so we've got two lots of oxygen bonds to be broken in your oxygen molecules. When we go to look at the products, don't forget that we're forming 1 mole of carbon dioxide, but what is often forgotten is that carbon dioxide has in fact got 2 lots of carbon oxygen bonds. Now let's go and look at the water. Water has got 1, 2, 3, 4 lots of oxygen hydrogen bonds. So the bonds to be broken are 4 lots of carbon hydrogen bonds and 2 lots of oxygen bonds. The bonds being made are 2 lots of carbon double bond oxygen and 4 lots of oxygen hydrogen. All we need to do now is to go to our table and get the values for breaking 4 lots of carbon hydrogen bonds and breaking 2 lots of oxygen bonds. We add all of that up together and that comes to a positive value, because remember, average bond enthalpies, you're putting in energy, it's got a positive value. So to break all of the bonds in the reactants completely requires plus 2,640 kilojoules per mole. However, when we make the new bonds, if we add all of these together, so that was 2 lots of carbon oxygen bonds and 4 lots of oxygen hydrogen. When you add all of that together, because energy is released, that is minus 3,338 kilojoules per mole. So bond breaking is plus 2,640 and bond making is minus 3,338. If we now use Hess's law and we look at these arrows, so if we call this one Tom, this one Dick and this one Harry, just like we did on our Hess's law, and we see which arrows are going in a clockwise direction, we can see that Tom and Harry are going in a clockwise direction and Dick is going off on his own in an anti-clockwise direction. So the unknown enthalpy change here, delta H, is equal to Tom plus Harry. And therefore delta H is equal to the sum of all the bonds that we break and added to the sum of all the bonds that we've made. But since that has a negative sign, we can say minus the sum, the bond enthalpies of all the bonds that we've broken. So we can apply this equation to any bond enthalpy data question. So now we'll apply Hess's law as we just did. So this is the sum of the bonds broken minus the sum of the bond enthalpies of both the bonds made, and the overall enthalpy change is minus 698 kilojoules per mole. And we'd expect that for a combustion reaction. It's ectothermic because heat energy is being released. So in general, the enthalpy change for a chemical reaction is the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds made. Let's look at a different example now. Here we've got some hydrogen iodide, and this time we're looking to find the enthalpy change for reaction when hydrogen iodide, 2 moles of hydrogen iodide molecules break down to form iodine and hydrogen gas. So in this reaction we can see delta H is positive, it's endothermic. There's the reactants, here's the products. The products have got more energy than the reactants. If we now look at using average bond enthalpies or mean bond enthalpies, Again, here's our hydrogen iodide molecules. Hydrogen iodide molecules, we've got 2 moles of them. So we need to break 2 moles of hydrogen iodide bonds to get the gaseous atoms. The gaseous atoms then recombine to form our products, which is 1 mole of hydrogen atoms and 1 mole of iodine atoms. This time we need to put more energy in breaking the bonds here than the energy is released. So there's the energy going in to break the bonds, here's the energy being released when new bonds are made. We now put the values in for this reaction. So we're breaking 2 moles of hydrogen iodide bonds, so the enthalpy change for the reaction is equal to the sum of 2 times the bond enthalpy for hydrogen iodide, and we're making new bonds, so I'll put a negative sign there because we know this is exothermic, and that's the sum of the bond enthalpy for 1 mole of hydrogen and 1 mole of iodine. So the energy required to break 2 moles of hydrogen iodide bonds is plus 598 kilojoules per mole. The energy released when we form 1 mole of hydrogen molecules and 1 mole of iodine molecules is minus 436. So again, using Hess's law, these 2 enthalpy changes are going in the same direction. So this is the sum of the bonds broken, and this is bonds made. And there's our enthalpy change here. So these are going in a clockwise direction, and this is going off in an anti-clockwise direction. So again, delta H is the sum of the bonds broken. We put a negative sign in here because the bonds made is exothermic, so that's minus the sum of the bonds made, and therefore the enthalpy change for this reaction is plus 11 kilojoules per mole. So we can see it's an endothermic process. The products of the reaction have got more energy than the reactants, and for every time you get a bond enthalpy question, remember you can short, rather than use the enthalpy cycle, you can simply summarize the equation with the enthalpy change is equal to the sum of the bonds broken in the reactants minus the sum of the bonds made in the products. So the example we're going to look at here is from page 20 in your independent study booklet from a past paper question, and it's really important here that you read the question carefully. So because this is AS, it gives you the structure of the compound ethanol, which is an aldehyde, and they've drawn the structure fully for you. And then again, it's really important to look at the stem of the question, and it tells you that when ethanol burns, it burns in 2.5 moles of oxygen to give 2 moles of carbon dioxide and 2 moles of water. The very first thing it's really important to do whenever you see you've been given bond enthalpy data, mean bond enthalpy data, is to draw out the structure of everything in the reactants and everything in the products, showing clearly each individual bond. So they started doing this for you, and then underneath they gave you the balanced equation. So what you can see I've done here is to write out that you have got 2.5 moles of O double bond O. There is not a red herring in the question here with O single bond O. With O double bond O. And when that reacts to form 2 moles of water, so draw out your 2 molecules of water, displaying all 4 oxygen hydrogen bonds, and 2 moles of carbon dioxide, showing all 4 C double bond O's. Now in this question it's quite easy to dive in and just to use the overall equation delta H equals bonds broken minus bonds made. However, here they've broken it down for you. So it says calculate the enthalpy change which occurs when all the bonds are broken. And what you must do is write out, explicitly show which bonds have been broken. So I've done it slightly differently than in the mark scheme here. What I've done is to go through each individual bond and write it down, and this is really, really important that you do this. So here I've got 3 lots of carbon hydrogen bonds, 1, 2, 3. Look at the data, that's 3 times 413 kilojoules. I then go to my next bond, which is a carbon-carbon, and cross that off, and that's 1 lot of 347. I then see that I've got a carbon-oxygen bond, so I cross that one out, and that is one lot, 1 times 736. Notice here that double bonds, multiple bonds, require much more energy to break because you've got almost twice the electrostatic attraction to overcome. So double bonds require a lot more energy to break. So, and then I've got another carbon hydrogen bond here. So in the mark scheme they included that. So in the mark scheme they said 4 carbon hydrogens, but I've treated them all separately. Come out with the same answer anyway. And then the next reactant here we can see is the oxygen. We've got 2.5 moles of oxygen gas. So I can now tick that off. And then I show the examiner that I've got the data from the data sheet, and finally I can sum it all together, so we get a value of plus 3,980 kilojoules of energy needed to break all of the bonds in the reactants. We just go back, was 3,900. The next part of the question asked you what is the enthalpy change when all of the bonds in the products shown in the above equation are formed. So we've got 4 lots of oxygen hydrogen bonds, which is 4 times 464, as you can see from here, and 4 lots of carbon oxygen bonds, which is 4 times 736. We add those together and get a value of 4,800. Now don't forget that bond making is exothermic, because you're releasing energy because there is a massive electrostatic attraction when all those nuclei attract all of those electrons. So that's an exothermic value. However, in our equation it says calculate the enthalpy change for the complete combustion of ethanol shown in the equation above. So if we were to apply this to our equation, which is the enthalpy change for the reaction is the sum of the bonds broken minus the sum of the bonds made. Remember that negative sign there accounts for the fact that bonds made is an exothermic reaction. So that negative sign already takes that into account. So from the last part we found out that the enthalpy change for the bonds broken, take away 4,800 gives us a grand total in the enthalpy change for this reaction of minus 820 kilojoules.